Now we are going to see energy stored in a capacitor or energy of a capacitor. So here, when the battery is connected across the capacitor, the negative of the battery pushes the electrons towards this terminal, right terminal, and right plate of the capacitor. Then the right plate pushes the negative charges to the plate in the left side. So similarly, it's so here when this side is positive, this becomes positive side, this becomes negative. Then automatically opposite side becomes positive. Okay, other side becomes positive. You know that electrostatic induction. So when negative charges reaches here, positive charges will be developed here this side. Then automatically negative charges will be developed here. Then opposite side, other side, positive charges will be developed. So by this way, charges will be developed. See here, to transfer the charges from one plate to another plate, this battery is supplying energy or doing work. The work done by this battery is stored as energy. So that is the energy of the capacitor. Okay. Now first we can see a small work done dW while charging the plate by a small charge dq. For example, dq charge is the charge supplied by the battery. Then the small work done dW is given by V into dq. Okay, so voltage into charge is equal to work done. Okay, but you know the formula, C is equal to what? C is equal to Q by V, or V is equal to what? Q by C. So substitute this value, Q by V, Q by C dQ. This is what? dW. Small work done is given by this one. Okay, so what's the total work done? Initially charge in the plate is 0. Final charge is Q. Okay, charge is 0 initially. Then after supplying the charges, the final charge becomes Q, for example. Now total work done is given by W is equal to integration of dW. This is equal to 0 to Q. Initial amount is 0, final charge is Q, then Q by C dQ. So this is equal to what? As C is constant, we can take it out, 1 by C. What's the integration of this one? Q dQ. X, this is the form of X dx. What's the integration of X dx? X squared by 2. So similarly here, this becomes Q squared by 2. Limit is what? 0 to Q. Substitute this value, upper value, and minus lower value. This becomes what? Work done is equal to 1 by C Q squared by 2 minus 0. Okay. Or we can write this is equal to half Q squared by C. This is work done. This work done is stored as energy. So that's why it is called as what? Energy stored in the capacitor, UE. Okay. What do you know that formula? C, another formula is what? C is equal to what? No, C is equal to V is equal to Q by C, or C is equal to Q by V. From this one, Q is equal to what? Q is equal to C. Substitute this value here. So this becomes of CV whole square by C. So this becomes of C squared V squared by C. Again, cut 1 C. Okay, so now this becomes of C V squared. This is the energy stored in a capacitor. So this is a very important formula, and derivation also. We can have 3 mark question or 5 mark question. Based on this formula, you can have sums in choose the correct answer like that. Okay. So next we are going to see capacitors connected in series and parallel. You can see energy density energy density in a capacitor. So what's the formula we are seeing? So energy of the capacitor, UE is equal to what? Here this is the symbol is what? Small UE. Okay. U is E is equal to what? Half C V square. Okay. But you know the formula for C. C is equal to what? Epsilon naught A by E. Moreover, what's the V value? E is equal to V by D. E is equal to V by D or V is equal to ED. Okay. Now substitute these two equations in the first equation. Substitute these the two value here. So UE is equal to half epsilon naught A by D. This is for C. D squared by E D whole square. Okay. Or we can write E squared into D square. Okay. Can you write like this? Next. 1D. This will be cut off. Now this becomes half epsilon naught. Then right. Epsilon naught. This is here what? E squared. This is what? E squared. AD. Right. AD. Am I correct? AD. Half is the epsilon is the A D. I am writing this AD together. E squared is written here. Okay. What is A into D? You know, capacitor. This distance is what? Small d. The area of each plate is what? A. So area cross section A into D gives you the volume of this space. Volume. Okay. Then we can write, so UE by AD. AD is nothing but volume. Okay. So total energy divided by total volume is equal to half epsilon naught E square. Or this can be written as small UE is equal to. This is called energy density in a capacitor. So UE is equal to half epsilon E square. So this is the energy density of a parallel plate capacitor. Next we are going to see effective capacitance of capacitors which are connected in series and parallel. In series. Here we are going to see the effective capacitance of capacitors connected in series and parallel. There are three capacitors. I have to say one thing. The symbol for capacitor is two parallel lines. You see how this is a symbol for capacitor. Sometimes I can use this also. This also. So here you have to note a difference. For battery, you got to put like this. This is for battery. This is battery. This is for capacitor. These are for capacitors. So here don't get confused. Battery one line will be lengthier than another one. But here both lines will be parallel. Sometimes it may be like this. This is electrolytic capacitor. This is parallel plate capacitor. Okay. So here we are having three capacitors C1, C2, C3 in series across a battery or a battery is connected. Okay, plus minus. The capacitors of first one is C1, second one is C2, third is C3. As soon as that battery is connected, so electrons will be pushed towards the right side of the C3 plate. The electrons will push towards the right side of the C3 plate. So here the electrons will become here. Okay. At the same time, the left side of the C3 will be pushing negative electrons towards the right side of C2. So this becomes positive, this becomes negative. Next, the C2 will be pushing negatively charged electrons towards the right side of C1. So the electrons will be coming here, so this side becomes positive, electrons will be coming here. At the same time, the C1, the left side of the C1 will be pushing electrons towards the positive terminal, this side becomes positive. Okay, so by this way, displacement of electrons will be taking place through these capacitors, so that charge in each plate is same. In series, the charge in each capacitor is same. Okay, next. So here, the potential is different. You know the formula C is equal to what? Q by V. So this is a general formula. As that even the charges are same. C is different, so V will be different. So what potential across this one is what? V1, V2, V3. Okay. So total potential is equal to what? V is equal to V1 plus V2 plus V3. Okay. So here what is V? V is the total voltage across the combination. So here from this one C, V is equal to what? Q by C. So total charge Q, total capacitance of this combination CS. What is V1? In place of V1, Q by Q is same in all the capacitors. Q by C1. This is. What is V2? V2 is nothing but Q by C2. Okay, Q by C2. Similarly, V3, Q by C3, which is common in all the terms. Q is common, so take Q out. 1 by C1 plus 1 by C2 plus 1 by C3. This is by Q by CS. We can cut Q to Q. So this becomes 1 by CS equal to 1 by C1 plus 1 by C2 plus 1 by C3. So what do you understand from this one? The reciprocal of effective capacitance of the series combination is equal to sum of the reciprocal of individual capacitances. Okay. So here, suppose we are having all the capacitors are having equal capacitance. Then suppose we are connecting n capacitors in series. We can write 1 by CS equal to 1 by C plus 1 by C plus 1 by C dot dot n capacitors. So this becomes what? N into 1 by C. Suppose we are having two capacitors, 2 into 1 by C, 3 into 1 by C, 4 n. So n. So here 1 by C is equal to, so C is equal to what? C by n. Okay. You can have sums based on this formula. So you get the of this one. Next we are going to see in parallel. Suppose capacitors are contained in parallel. What's the effective capacitance? See here. In parallel, capacitors are connected in parallel. This here, suppose this is a battery. Here we are having a capacitor. Here another one. Here we are having third. All are connected in parallel. What will be parallel connection? C1, this is C2. We can put this C3. This will be positive, this will be negative, positive, negative, positive, negative. Okay. If identical similar sides are connected to one terminal, then the type of combination is called parallel combination. Okay. So here the voltage of the battery is V. Here potential across each capacitor is same, but charge will be different. Suppose Q amount of charge is coming here. So it's you know the formula C is equal to Q by V. So potential is same. As C is varying, Q V also varying. So here the charge is Q1. Here it may be Q2. Here it may be Q3. So total charge from this battery is Q, for example. So Q is equal to Q1 plus Q2 plus Q3. Okay. So from this one, what is Q? Q is equal to CV. Okay, so total charge is equal to total capacity P for parallel. So CPV Q1 in place of Q1 we can write Q1 C1V. About Q1 so Q1 is equal to what? C1V plus Q2 C2V C3V. So it is common in all the terms. V is common. Take V out. C1 plus C2 plus C3. So CPV. So V is cut off. We can cancel. We can cut V on both sides. So CP becomes C1 plus C2 plus C3. Similarly, suppose you are having n capacitors. Each capacity is equal to 1 and half. Then we can write Cp is equal to C plus n capacitors, n times. So this becomes Nc. So Cp is equal to Nc. So here in parallel combination, effective capacitance is equal to sum of the capacitance of individual capacitances. Usually the effective capacitance or net capacitance will be larger than the highest value of the capacitance. Suppose this is 1 microfarad, this is 2 microfarad, this is 3 microfarad. So what's the capacitance of this? What's the value of Cp? Cp is equal to what? 6. So the effective capacitance is 6 microfarad. So this effective capacitance is higher than the highest value of the individual capacitance. Okay. So this is something about capacitors in series and parallel. Okay.